Welcome back, everyone. And the second talk of today is given by Federico Vigolo from Weizmann Institute in Israel. And the topic of the talk is asymptotic expander graphs.
Okay. Thank you for the introduction and for the invitation. It's very nice to speak at the Symmetry seminar here. Well, it would have been nicer to be in Australia, but we do what we can. So let's discuss a bit the plan of the talk. So this talk is about asymptotic expander graphs, which are a generalization of the definition of expander graphs. So I will start off with a bit of, if you want some introduction about, classical expander graphs, because I want to reach to the asymptotic expanders. That is the part where I have new math to tell you about. And in the middle, in the abstract, I promised that I want to give a non-technical talk. And the problem is that asymptotic expander graphs are motivated by some questions about analysis and sister algebras. So I added this motivation section, which I plan to be very sketchy, so I will not give the definitions, and this will just be a parenthesis where I would say some motivation. So even if you get lost in the middle, don't be worried, because then we start afresh here. So this is just some motivation that if you don't follow, it's not a big problem. Also because I will not really explain it. And then we get to the part that we care about. Okay, so let's start. In the abstract, I give a slogan definition of expander graphs, where I say expander graphs are sequences of sparse yet highly connected finite graphs. So there are a few important words. So what are finite graphs? So we're just looking for finite things, but we want those finite things to be arbitrarily large. That is with many vertices. And so to get arbitrarily large finite graphs, then we pick sequences. So there will be some sequences of finite graphs satisfying some properties uniformly over the sequence. And then the important word is sparse, which just means uniformly bounded degree. And possibly the most important word is highly connected. And there are two ways of saying what highly connected is, and they're both very important for the study of expander graphs. And one way is to say that it's hard to disconnect them. So hard to disconnect, meaning that if you want to break them meaningfully, you have to remove a lot of edges. And then another way in which a graph could be highly connected is that it's easy to walk from one place to the other. So easy to walk around. In some sense that will become more precise later, more random walk kind of sense. And these two notions of highly connected are equivalent. And they're both very important to the study of expander graphs, because depending on which applications you have in mind, you might want to look at one aspect rather than another. So this is more combinatorial geometric, while the random walks is more analytics in its flavor. So I will not say much. Yes. Yes. Have to move the previous. There one. Excellent. So I will not say much about the applications. Just trust me that there are plenty of applications. There has been a lot of research on expander graphs, both in computer science, because, for example, they can be used for defining error correcting codes and random algorithms, hardness theory, and a lot of other things. And they also have a number of applications in pure mathematics, of which I am going to focus on their applications that are coarse embedding into Hilbert spaces. They provide obstructions to coarse embedding into Hilbert spaces, and this is relevant to the, say, coarse Baum-Kohn conjecture. And this is the analytic thing that we are going to discuss about later. And many more applications that we are not going to get into because that would be a talk on its own. So let's now start with an actual definition. So in this talk, G will always be some finite and unoriented simplicial graph. So prototypical graph. And we identify G with its set of vertices. By this, I mean that if I write that A is contained in G, means that A is a subset of vertices. And if I write the cardinality of G, means cardinality of a set of vertices, etc. And then the degree of a graph is just the maximum of the degree of its vertices. That's it. Okay, so now I can tell you what is one epsilon expander. So let epsilon be a positive constant. Then we say that G, finite simplicial graph, is an epsilon expander if we have that for every subset of vertices with cardinality at most half of G, then the size of its boundary is at least epsilon time the size of A, where here we mean that the boundary of a set is going to be equal to the set of vertices that are in the complement of A, but that are linked to some vertex inside A for so for some B in A. So this means that there is an edge. So that, for example, say that this is our set A, then its boundary is just going to be these three vertices, because each one of them is connected to something inside of A. Okay, so this is the boundary of A. Okay, so back to our definition. Our definition is that we fix some epsilon a priori, and then we ask that for every subset that is not too large, we have a sort of isoparametric inequality. That is, the size of the boundary must be linearly large with the size of the set. And this can be seen as a notion of highly connectedness. That is, it is hard to disconnect G, well, meaningfully. So, i.e., so if you want to break G into two halves, to split G in two, then you need to cut roughly epsilon times the total number of vertices. That is, if your vertex has 1 million vertices and if you want to cut it in two, then you need to still remove epsilon of 1 million, which is a big number. So they are hard to disconnect. In our slogan definition, this is our hard to disconnect definition. Okay, Any questions so far? By the way, if at any point you have any questions, just please free to unmute and ask. All right, and so this is what is epsilon expander, but we said that we are looking for sequences of expanders. And so here it is. The real definition is that a family of expanders, is a sequence of finite graphs such that the cardinality goes to infinity, and the degrees of these graphs are all bounded by some constant d. And they are all epsilon expanders. Yeah. With the same constant epsilon for every n. So, yeah, do such graphs exist? Do there exist sequences of expanders? And the answer is yes, because it's a result by Pinsker, for example, that let D be fixed, and then a random sequence Gn of connected irregular graphs is almost surely a sequence of expanders. That is a family of expanders. Okay, but so expanders exist, but for our application we need concrete examples. And this is one of those annoying instances where the generic element is of a certain kind, but then if you actually try to write down a sequence of graphs, chances are that they're not going to be expanders, because yes, it's just because of the boundedness of our minds. We are not random enough. So most of the nice sequences of graphs you are going to encounter are not expanders. Like, because if you have a cycle, for example, then it is very easy to cut it because you just need to remove two edges and then you can break it in half. So if the cycle gets large, then it's very much not highly connected. And so also anything that looks like a manifold, like any triangulation of a manifold, if it has enough many vertices, it will be very easy to disconnect, because disconnecting it would be selecting a n-1 dimensional manifold, which has volume that tends to 0 if the triangulation is fine enough. So all the nice graphs, in some sense, appear not to be expanders, while the generic one does give you expander. And for the application, we really need some concrete examples. And to produce concrete examples, it is useful to use the other point of view on high connectedness, this more random walkie kind of approach. And so this is what we do now. We consider an averaging operator. And we have an operator that goes from the space of functions from vertices to R, so real valued functions on the set of vertices, and we define it by A of f, where f is a function and A of f is the image function, and evaluated at a point V will be equal to the average of the values of f among the neighbors of V. So it will be 1 over the degree of V of the sum from the neighbors of f of W. That is, when I want to evaluate here, then I just take the average of the values of f around all the neighbors. Okay, so this is just an operator on functions. And to make things simpler, this operator can be easy to compute in some cases. Well, it's always easy to compute, but in some cases it's easier than in other. In particular, if G is a D-regular graph, then it is easy to check that this operator, this averaging operator, is nothing but the adjacency matrix rescaled by 1 over D, where the adjacency matrix is this is the G times G matrix, square matrix, where you put 1 at a coordinate ij, where if the ith vertex is connected with the jth vertex and 0 otherwise. So that you have a matrix with, well, let's say 0 in the diagonal, and then a bunch of 1s where you have, so Ej is 1 if and only if the ith vertex is connected with the jth vertex. And so for each column, you're going to have D1s because it has D neighbors. And also each row will have D1s. More precisely, A is a symmetric matrix. And then you rescale it by 1 over D, so that then if you take the sum of a 1 row, then you get an actual average because you have D1s and then you average by 1 over D. But the bottom line is that we can write our operator just as a symmetric matrix. And in particular, we know that it is diagonalizable and it has real eigenvalues. Which we write as lambda 1 greater or equal than lambda 2 greater or equal than lambda 3, etc. And it is easy to check that since this is an average, then the first eigenvalue is at most 1, and it actually is equal to 1 because the constant functions are preserved. So this is a matrix that fixes the constant vector, the vector 1, 1, 1, 1, 1, 1, and so the first eigenvalue is equal to 1, and then all the other ones are smaller. And the interesting thing for us is that this theorem of Alon, Milman, and Dodge, which says that pick a sequence of, well, sequence Gn of D-regular graphs then this is a sequence of expanders, is a family of expanders, if and only if there exists some positive constant delta such that the second largest eigenvalue is smaller or equal than 1 minus delta for every n in n. That is, this is the second largest eigenvalue of the operator A associated with the graph Gn, with the nth graph. So it should be lambda 2 of Gn. And if we know that for all of them, for every n, there is a uniform gap here, there is distance at least delta, then we're getting expanders. And this is an if and only if. And in fact, this is called a spectral characterization of expander graphs, because by examining the spectrum of some operator, you just need to check whether there is a uniform gap between the largest and the second largest eigenvalue to decide whether your family of graphs are expanders or not. And I'm saying that this is a way of formalizing the fact that it's easy to walk around the graph, because, remark, this implies that the random walk implies random walk on expander graphs converge exponentially fast to the constant functions, to constants, and the rate of exponential convergence is uniform. In n. Why is this? Because the random walk on the graph just means that you start at the point and then you walk uniformly at random. Like you choose one of your neighbors uniformly and you walk there. And what does this have to do with the operator A? Well, if you start off with a function f and you see it as being the probability of being at a specific vertex, and then you do like f of a vertex is the probability to be at that vertex, and then you do one step of the random walk, then you're going to get a new probability distribution that is what is the updated probability of being at any given vertex, given that you started off with probability f and you did one step. And what the functions that you get is nothing but the averaging operator A applied to the function you were starting with. This is easy to check. So in particular, if you start your random walk from one vertex, this means that you start off with probability 1 at that vertex and 0 everywhere else. And then if you do n steps of the random walk, the probability of being at the various vertices is governed by the function A of n of your starting distribution that was the delta function on a vertex B. And in particular, if A has a spectral gap, this function will converge exponentially fast to being equidistributed. So in this sense, this spectral characterization of expansion can be seen as the analog of being easy to walk around on the graph. Any questions so far?
So far, so good, I would say. Excellent.
Then now let's go forward, because I started this slide by saying that this will give us a way of constructing examples of expanders. And so here it is. Here have a construction. So let gamma be a finally generated group. Finally generated, and choose a chain of finite index subgroups. So finite index subgroups. Okay, now I know that in Newcastle, profinite things, totally disconnected groups are very much of a thing. So I would just say that you can get a profinite tree, a coset tree. Coset tree T, that is, we have our gamma, and then we have some cosets, G gamma 1, H gamma 1, etc. And then we have the second layer of cosets. So there is G gamma 2, H2 gamma 2, so G2, H1. And so we construct our nice tree. So that at this level we have the set of coset gamma over gamma 2, while at this level we have the cosets gamma over gamma 1. And now gamma acts on the tree, and it also acts on its boundary. Well, yes. So, yeah. Gamma acts on the boundary at infinity of the tree. And we see this boundary at infinity as a Cantor set with a probability measure. Where the probability measure is just given by the uniform probability. I mean, it's given by pushing up the uniform probability, the uniform probability on the set of cosets. Okay, and now we have an easy consequence of this spectral characterization by Alon, Millman, and Dodge is that the sequence of coset graphs that is, we have fixed generating set and we look at the Schreier coset graphs. So this is a sequence of finite d-regular graphs, and these are expanders if the action on the boundary has spectral gap. Where spectral gap in this case means that we have an action on a probability space, so we can use it to induce an action on the space of function on that space, or space of measurable functions, or better on the L2 of that space by precomposition. So we have our nice action by precomposition on the space of square integrable function, and we have an associated averaging operator AS that again goes from L to infinity t on itself, and which is defined by taking the average, so 1 by s. Well, let's say that AS applied to a function f is the average of the translates of f over the generating set. And now this time, this is just analogous of before. The only difference is that we are on an infinite dimensional vector space. So the analog of symmetric in this case is self-adjoint. And this is indeed a self-adjoint operator. And so it has a real spectrum, and it has a first eigenvalue and the second eigenvalue. And so with spectral gap means that the second largest eigenvalue of the operator AS is strictly smaller than 1. While the largest eigenvalue will be equal to 1 because, again, this operator is an average, and so it preserves the constant functions and everything else is flattened a bit. And we ask by how much is flattened. And we say that the action has a spectral gap if it is flattened by some non-trivial amount. Okay, so we say that this construction is telling us that a sequence of Schreier coset graphs can give expander graphs as soon as you know that the action on the boundary at infinity of the coset tree has a spectral gap. And so, for example, if gamma has property T, Kashdans T, then any such chain works, because Kashdans property T are precisely groups for which every action has spectral gap, in a sense. So this was a very easy consequence of the theorem of Alon-Millman, and a slightly less easy but still true, and not very hard, is that the converse is also true. So this is an if and only if. That is, if you have a chain of subgroups, then the Schreier coset graphs are going to be expanders if and only if the action on the boundary at infinity of the tree has spectral gap. So this will give us some construction. What comes next? Okay, and now comes the analytic part. Okay, One reason to care about expanders, as I was saying, is motivated by what is called as the Baum-Kohn conjecture. Or here you can actually see, well, I don't think conjectures in plural. And there are some conjectures that predict that some assembly maps between some K-theories of sister algebras are isomorphism. That is, Baum and Kohn define an assembly map and they conjecture that this assembly map should be an isomorphism. And I'm not going to define any of this. And I'm just remarking on the S that there was an original Baum-Kohn conjecture which admits many generalizations. Most of which are now known to be false, precisely because of expanders, we'll see later. And one of the generalizations that we're going to care about for this talk is the coarse Baum-Kohn conjecture. So I write BCC for Baum-Kohn conjecture. This is a statement about metric spaces. Well, algebras associated with metric spaces. Well, the original Baum-Kohn conjecture was more only for groups. The coarse Baum-Kohn conjecture is for all metric spaces, and it relates with the original Baum-Kohn conjecture via the Cayley graph. You can study group as metric spaces with the Cayley graphs. But I'm not going to say anything about this conjecture for real. I would just say that it's a theorem by you that if you have a bounded geometry discrete metric space which admits a coarse embedding into a Hilbert space, this is the important notion, where a coarse embedding is a slight weakening of a quasi-isometric embedding. So if you have a coarse embedding into a Hilbert space, then the metric space you were starting with satisfies the coarse Baum-Kohn conjecture. And this is possibly the strongest tool that we have at the moment to try to prove the Baum-Kohn conjecture for some classes of metric spaces. And so we know that Baum-Kohn conjecture is true for every metric space that coarsely embeds into a Hilbert space. Now it is an easy fact, which is like really easy to prove once you know the Arnold-Millman theorem, is that expanders do not uniformly coarsely embed into Hilbert spaces. That is, I mean, each finite graph does embed into Hilbert space coarsely because it's just trivial, but the important word here is uniformly. That is the distortion of the metric, the metric distortion of embeddings of the graphs in an expander families into Hilbert spaces becomes worst. Well, worsen becomes worst, is worst the larger the graph. What I'm trying to say is that if you have a family of expanders, each single graph trivially coarsely embed into a Hilbert space because it is coarsely 1 point. Up to coarse equivalence is just 1 point. But then if you look at the whole family, then you cannot find embeddings into the Hilbert space that are uniformly distorted. Like the larger the graph, the more you will have to distort it in order to coarsely embed into a Hilbert space. So in particular, if you have one nice metric space that contains inside a family, an isometrically embedded family of expanders, this implies that this space cannot coarsely embed into a Hilbert space, because a coarse embedding of this big metric space would give you some uniform coarse embedding of all the graphs in the expander family, which cannot exist. So this is telling us that expander graphs are an excellent candidate for providing spaces that do not coarsely embed into Hilbert spaces, and so that can a priori, I mean, for which we do not know whether the coarse bound-con conjecture holds true. And
just a question.
Please go ahead.
So when you're saying a graph embedding into a Hilbert space, does it mean like I'm equipping the graph with the path metric and then I want the embedding? Yeah, so that's the kind of embedding, yeah. Okay,
yes,
thank you.
Yeah, I should have said that. I think of graphs as metric spaces because I always equip them with the path metric. And by coarse embedding, you can think of quasi-isometric embedding. And by uniform coarse embedding, you can think of quasi-isometric embeddings where the quasi-isometric constants are the same throughout the family.
Yeah, thanks.
Okay. Thank you for the question. Okay, and then there is a theorem by Gromov and then improved by Ozaida that there exist finally generated groups whose Cayley graphs coarsely contain families of expanders, or even isometrically in the case of Ozaida. And you might have heard these groups referred to as Gromov monsters. It is a fairly famous class of groups that are precisely groups that contain expander graphs in some sense. Okay, so we do have groups whose Cayley graph do not coarsely embed into Hilbert spaces. And then it is a non-trivial theorem by Hickson and Hickson-Lefort-Skandalis that these groups can indeed be used to construct counterexamples to the bound-con conjecture and the coarse bound-con conjecture. So indeed, this version of the bound-con conjecture is false, and pretty much the only way to prove that this is false is by using this technique, is by using these expanders embedded into Cayley graphs or what. Anyways, by using expander graphs to note that the statement which I didn't give you is false. Okay, so this goes for motivation, but what we want to take away from this is that, yeah, how am I doing on time? I'm not doing well. Okay, the reason why I got into this discussion is that the key point in the theorem of Hickson and Lefort and Skandalis providing counterexamples is that you can consider a mean value operator on expander graphs. Well, that is PGN. Again, that goes from functions from the graph. But this time we go just to R and we take, and this is the operator that associates the mean. This it sends F to just, yes. And F of here. Yes, I'm just taking the mean value. So this is a nice operator. And the key point in the above theorem is that, let me see, how did I write it down? Yeah. Okay, and the key point is that if Gn is an epsilon expander, then our averaging operator, the ones that we had before, will converge exponentially fast to this mean operator. And this is just restating what I was saying before, that if you do the random walk, then it will converge to the uniform probability very quickly. This is just a different way of restating the same result. But the important thing comes later. Yes, so again, the motivation is that the second largest eigenvalue, I mean, basically, yeah, this is just what I said before. But the easy consequence, if I had defined what these things are, is that if we have now a sequence of expanders, and then we can consider the sum of all these averaging operators that go inside R to the n, and we call this big operator, we call it P. And the thing is that this operator P belongs to the row algebra of the union of expanders. Okay, I did not say it, but the course bound-Cohen conjecture, the bound-Cohen conjecture for metric spaces involved this notion of the row algebra, which again I'm not going to define. And so this, what I'm saying here is that if you have expanders, then this big operator P will belong to this row algebra. And it is what is called a non-compact cost projection, which is, again, something. And the important thing is that if you then do a fair bit of more work, then you can show that this operator P does not belong to the image of the assembly map. So the assembly map is not surjective, so it is not an isomorphism. So the coarse-bound-Cohen conjecture is false. Now, I'm just saying these words, but I don't expect anyone to get anything out of this. I'm going to stop talking about operators soon. I think, yeah. The point is that I'm getting to the questions that motivated the definition of asymptotic expanders. So let me just be a little bit more precise here about this operator P, etc. So I was saying that the important object is the row algebra, which is some C star algebra of operators, which is denoted by C star of the union of Gn. And it is a subalgebra of the C star algebra of bounded operators. Consider all the bounded linear operators on a Hilbert space H, where H is just the Hilbert sum of these spaces of functions on the graph G. That is, before we were looking at the spaces of functions from the vertices of a graph into R, and so this is a finite dimensional vector space. And now we want to take the sum of all these finite dimensional vector spaces to get an infinite dimensional vector space, and this is our Hilbert space H. And then we can look at all the linear operator of H inside itself, and this is the space B of H, and then the bounded linear operators. And then the row algebra is some subalgebra of that algebra of operators. Okay. Okay, and the operator P, like in this context, the operator P, you can actually see it as the orthogonal projection to the subspace of H, consisting of the functions that are constant on each Gn. Yeah, I'm running out of time, so I think I will stop annoying you with analysis, and I will just say, yeah, let's just skip the rest of this, and let's just say that there is an easy classical fact is that every operator in the row algebra is quasi-local, which again, I'm not going to define, but this is an important word for us, quasi-local. And it is an important word for us because there is a fairly old open question, is the converse true? So is it true that that is, if you have an operator in B of H, which is quasi-local, does it belong to the row algebra? This is an open question that is interesting to people who do C-star algebras. But we have also a sub-question that is, how about P? That is, every time we have a sequence of graphs, then we can consider this operator P, that is just taking the average on each single graph. And this will always be a bounded operator. And sometimes it will be quasi-local, sometimes it will not be. And sometimes it will be in the row algebras, and sometimes it will not be. And we're asking, is it true that P is quasi-local if and only if it belongs to the row algebra? That is, we are specializing the big open question to a sub-open question where we only care about one specific operator. Okay, and this is where asymptotic expanders come in. And actually, this is because I said that quasi-local is important, and we are lucky because quasi-locality, when restricted to the operator P, can be described explicitly. So we say, it's an easy fact, it's easy to show that if you have a sequence of finite graphs, then the projection P is quasi-local if and only if you have that for every epsilon, there exists some R, some reduced R large enough, so that if A and B are subsets of vertices of Gn, such that the distance between A and B, again in the path metric, is at least R, then either the size of A is smaller or equal than Gn, or the size of B is smaller or equal than epsilon, the size of Gn. That is, quasi-locality is saying that for every positive epsilon, there exists a radius large enough so that if you pick any two subsets that are at least that far apart, at least one of them must be very small, must be epsilon small with respect to the size of the graph G. Okay, and so we can take this as our definition of quasi-locality. Because we will only care about quasi-locality for this averaging projection. And if you want, it is a very easy exercise at this point to show directly that if you have a sequence of expander graphs, then the averaging projection is quasi-local. That is, expander graphs do satisfy this property that whenever you fix an epsilon, this is not the expansion constant, so let me pick a different name. Not call it epsilon, let's call it eta. Just to say, it's not the expansion constant, it's some different constant. Okay, if you have a sequence of expanders, then it is easy. Like the fact that the boundary is linearly large means that if you take the boundary of radius R, then you are increasing the size exponentially fast. And using this fact, it's very easy to show that this condition does indeed hold for expander graphs. That is, once you fix a parameter, then two subsets that are distance at least R, it means that the R neighborhoods must be, the R neighborhood of one must be disjoint from the other. And since the R neighborhood grows exponentially fast with the exponent depending on some fixed epsilon, then it must be, the other set must be small. At least one of the two sets must be small. Otherwise, there wouldn't be enough room to fit in the R neighborhood. So if you want, this is an easy exercise. Okay. I'm really around for time. So we said it's an easy exercise to show that expander graphs are, for expander graphs, the operator P is indeed quasi-local. As a warm-up question, we have, if you have a sequence of graphs, and you also know that this averaging operator P, the mean operator, is quasi-local, does this imply that Gn is a sequence of expanders? The answer is easily no. And one easy example is as follows. You just pick one family of expanders. So pick Gn expanders. And now you make them into not expanders by adding some small tails. Say you add one segment of length about, say, 1/n, the size of Gn. Now, this small tail is small, but as you go along the sequence, it increases its length. So this is breaking the expansion condition, because you can find big sets with very small boundary because you cut it just by removing one edge, so against expansion. But it still satisfies this quasi-locality condition because the thing you're adding is just very small. So if you look at things about, if you look at size is up to some constant times the total size of G, the thing you added is negligible. So yeah, so this gives you an easy counterexample to the warm-up question. And so one can ask, so what are the graphs for which the operator P is quasi-local? Well, then it is a theorem by Lee, Novak, Spectral, and Zhang that says that the following. Suppose that you have a sequence of graphs with degree less or equal than d. And then the sequence, well, then P is quasi-local if and only if the following holds true. For every constant epsilon alpha that is less than a half positive, there exists an epsilon such that for every, well, such that the size of the boundary of A is at least epsilon A for every subset A in G with size at most half size of G and at least alpha times the size of G, where this G should be Gn. Okay. Now, this should look familiar. That is, this was the isoparametric inequality that we had in the definition of expanders, and this as well we had in expanders. This is the new bit. So this is the only thing where this notion, so this notion is basically saying that the graphs G and R expanders, at least on a large scale. That is, this is the new bit from the definition of expander graphs. And then we say, as a definition, Gn satisfying these conditions are called asymptotic expanders. And if you want, the definition is given so that i.e. asymptotic expanders if and only if P is quasi-local. So we have an analytic definition, something that we cared about from an analytic perspective, which is why I carried you through the last few slides. And this analytic notion is equivalent to some more geometric one, more combinatorial one, which is the one outlined here. And I should actually say that the definition of asymptotic expanders is not just for graphs, but it is for sequences of metric spaces. But I think that I ran out of time, so we'll not get into that. And yes, and let's try to do something with these asymptotic expanders. Oh, well, yeah, I have to give you an example. Okay, I gave you here a trivial example of some graphs that are not expanders, but are asymptotic expanders. So asymptotic expanders, not expanders. But this is not a very exciting example. I want to give a more interesting one. And the more interesting one is, again, in the form of Schreier-Coset graphs. So again, we have gamma and a chain of finite index subgroups. And then again, we have 3T, the coset 3. And the action of gamma on the T, the boundary of T, the boundary at infinity. And the result is that the Schreier-Coset graphs are asymptotic expanders if and only if the action on the boundary is what is called strongly ergodic, which I wanted to define, but I don't have time. So let's just say that it's something that, in a sense, looks like this condition. Anyway, this is a relatively standard notion in dynamical systems. Okay, so then there is a theorem by Miklos, Abert, and Elek that says that, well, first off, if the gamma I, if gamma n are normal subgroups of gamma, then yes, then the action on the boundary is strongly ergodic if and only if it has a spectral gap, which, to remind you, is at the beginning of the talk, I was said that this is the condition necessary to produce expanders. So it is saying that if instead of Schreier graphs, we actually consider Cayley graphs of finite quotients, then such objects are going to be asymptotic expanders, that is strongly ergodicity, if and only if they're going to be actual expanders. Okay, this is not very good, but things change if we are not assuming that the subgroups to be normal. And in fact, they also show that there exist sequences, well, chains, gamma n, of non-normal subgroups, such that the action on the boundary is strongly ergodic, but has no spectral gap. Which means that if you do the Schreier graphs of that sequence, then you get asymptotic expanders that are not expanders. And as a remark, let me just say that their argument is probabilistic. They construct the chain by taking random covers of some graphs. And I think it would be interesting to have explicit examples. There is some explicit chain of finite index subgroups so that the induced action on the boundary is strongly ergodic but does not have spectral gap. Okay, how am I doing on time? Oh, I run out of time. So let me just...
You can go about a few minutes over.
Yeah, let me just finish with this slide here. Okay, so I started the analytic discussion to reach to the question. And the question was, is it true that a bounded operator belongs to the row algebra if and only if it is quasi-local? And then we restricted that question to the mean operator, the operator P. So this is back to our question. Is it true the operator P belongs to the row algebra if and only if it is quasi-local? Then we can break up this question, because now we know that P is quasi-local if and only if asymptotic expanders. And so the question breakup is as follows. So say that you have Gn asymptotic expanders. Does there exist, can there be a coarse embedding into Hilbert spaces? And there are possible outcomes, yes or no. If there was a coarse embedding into Hilbert space, then it would follow from standard techniques that P does not belong to the row algebra. And so we would have solved the small question, which also solves the big one because it's in the negative. If not, if it is not true that, I mean, if asymptotic expanders do not coarse embed into Hilbert space, then we remain with the question, well, but does it belong to the sister algebra? So this is again a question. Basically, we didn't do anything. Well, if for some reason we manage to solve this directly in the negative, say this is no, well, then we just the same case as before. Well, if we can prove that P belongs to the row algebra, then again, it's going to be a non-compact ghost projection in the row algebra, which are those words that I did not define that should imply that there exists more counterexamples to the coarse bound-con conjecture. So that is the question. So do there exist more counterexamples to coarse bound-con conjecture? And the point of this talk was that in a joint work with Kukro, Lee, and Zhang, we show that there do not exist coarse embedding to Hilbert spaces. And yes, it is true that the averaging operator belongs to the row algebra. And yes, it can produce more counterexamples of the coarse bound-con conjecture. And the main theorem that allows us to do that, which I will state and then I will stop, is that a sequence of graphs Gn is an asymptotic expander if and only if there exists an exhaustion by expanders. Which I will save you the definition of what this means because I'm out of time, unless you ask me to. But it's sort of saying that the picture is that if you have a sequence of asymptotic expanders, then they sort of look like a sequence of expanders with some extra noise added, which is more or less like the trivial example that we drew before, but it's a little bit more complicated, but not a whole lot more. That is, your sequence, your finite graphs have some expanders inside that get larger and larger. And so this is the theorem that we prove, and using this theorem and the control it gives us, we can answer these questions that were raised in the paper by Novak, Spectral, and Zhang. And I had quite a few more things to say, but I totally ran out of time, so I will stop it here. And please do let me know if you have any questions or would like to hear more about this. Thank you.
Well, I have just one simple question. Kukro is Anna or Evgeny?
It's Anna.
Thank
yes,
you.
Sure.
Okay, so thanks, Federico, for the talk. Do we have any other questions? Well, if not, let's thank Federico again. Hit your clapping reaction buttons or knock the table, whichever you prefer. And thanks everyone for coming.
Thank you.
Yeah, you.